Hello students, this is Usha from G.k.Jain High Secondary School. Today we are going to see the current electricity part 2 in 12th standard physics. In this we are going to learn about the Ohm's law and the color code for carbon resistors. Let us move on to the topic. Ohm's law. The Ohm's law can be derived from the equation J equal to sigma E. Let us consider a segment of wire length L and cross-sectional area A. When a potential difference V is applied across the wire, a net electric field is created in the wire, which constitutes the current. We assume that the electric current is uniform in the entire length of the wire, so the potential difference can be written as V is equal to E into L. The magnitude of the current density J is equal to sigma E. Substituting for E, we get sigma V by L. As we all know that J is equal to I by A, that is the definition of your current density. When you are substituting, we will get I by A is equal to sigma V by L. By rearranging the above equation, we will get V is equal to I into L by sigma A. The quantity L by A is called as your resistance of the conductor and it is denoted by R. So we know that the resistance is directly proportional to the length of the conductor and inversely proportional to the area of the cross-section from the equation which is derived. Therefore, the macroscopic form of Ohm's law can be written as V is equal to IR. So, the resistance is a ratio of potential difference across the given conductor to the current passing through the conductor. So, R is equal to V by I. The SI unit of resistance is ohms. Now, we can see the graph. The first graph shows the potential is taken along your x-axis and the current is taken along your y-axis. The current versus voltage is showing a straight line with a slope equal to the inverse of resistance R of the conductor. So material for which the current again voltage graph is a straight line through the origin are said to obey Ohm's law and the behavior is said to be ohmic. Material or device that do not follow Ohm's law are said to be non-ohmic, that is shown in the second diagram, that is the graph. These materials have more complex relationship between voltage and current. A plot of I against V for non-ohmic material is non-linear and they do not have a constant resistance. Next we go to the next topic, resistivity. The resistance R of any conductor is given by R is equal to L by sigma A, where sigma is called the conductivity of the material and it depends on the type of the material used and not on its dimension. The resistivity of the material is equal to the reciprocal of its conductivity. Rho is equal to 1 by sigma. The resistance of the material, then we can write it as R is equal to rho into L by A. So, the resistance of the material is directly proportional to the length of the conductor and inversely proportional to the area of cross-section of the conductor. The proportionality constant rho is called as the resistivity of the material. If L is equal to 1 meter and A is equal to 1 meter square, then the resistance R is equal to rho. In other words, the electrical resistivity of the material is defined as the resistance offered to current flow by a conductor of unit length having unit area of cross-section. The SI unit of rho is ohm meter. Based on the resistivity, material are classified as conductors, insulators and semiconductors. The conductors have lowest resistivity, insulators have highest resistivity, and the semiconductor have resistivity greater than conductors but less than insulators. Next, we will go into the next topic, which is resistors in series. This is the diagram shown over here. So, when two or more resistors are connected end to end, it is said to be in series. The resistors could be simple resistors or bulb or heating element or other devices. So, the diagram first shows the resistors R1, R2, R3 connected in series. The amount of charge passing through resistor R1 must also pass through resistors R2 and R3, since the charge cannot accumulate anywhere in the circuit. Due to this reason, the current I passing through all the three resistors is the same. According to Ohm's law, if the current passes through different resistors of different value, then the potential difference across each resistor must be different. Let V1, V2 and V3 be the potential difference across the ends of the resistors. Then we can write V1 is equal to I1R1, V2 is equal to IR2 and V3 equal to IR3. So the total charge is equal to sum of the voltages across the each resistors. So V is equal to V1 plus V2 plus V3, which can be written as IR1 plus IR2 plus IR3. Where I is common, we can take it out. So we'll get V is equal to I into R1 plus R2 plus R3. So this can be written as V is equal to I into RS, where RS is the equivalent resistor. So RS value is R1 plus R2 plus R3. When several resistors are connected in series, the total or equivalent resistor is the sum of the individual resistance. The value of equivalent resistance in series connected will be greater than each individual resistors. Next, resistors in parallel. Resistors in parallel when they are connected across the same potential difference that is shown in the diagram. So, let the total current I that leaves the battery is split up into three separate paths. Let I1, I2 and I3 be the current through the resistors R1, R2 and R3. Due to the conservation of charge, the total energy in the current I is equal to the sum of the current through each of the three resistors. So, I is equal to I1 plus I2 plus I3. Since the voltage across each resistor is the same, applying Ohm's law to each resistor, we will get I1 is equal to V by R1, I2 is equal to V by R2 and I3 is equal, that is I3 equal to V by R3. Substituting these values in the equation, we will get I is equal to, so V is common, we will take it out, so we will get V into 1 by R1 plus 1 by R2 plus 1 by R3. So I is equal to V by Rp, where 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Here, the equivalent resistor Rp of the parallel combination of the resistors. Thus, when a number of resistors are connected in parallel, the sum of the reciprocal of the value of resistance of the individual resistor is equal to the reciprocal of the effective resistance of the combination. Here, the value of equivalent resistor in parallel connection will be lesser than each individual resistors. Household appliances are also always connected in parallel so that even if one is switched off, the other devices could be function properly. Next is color coding for resistors. Carbon resistor consists of a ceramic core on which a thin layer of crystalline carbon is deposited. These resistors are inexpensive, stable and compact in size. Color rings are used to indicate the value of the resistance according to the rules that is given in your tabular column. 3 colored rings are used to indicate the value of the resistor. The first ring or significant figure of resistance. The third ring indicates the decimal multiplier after them. The fourth color, silver or gold, shows the tolerance of the resistor at 10% or 5%. If there is no fourth ring, the tolerance is 20%. For the resistor shown here, in the diagram, it is shown the first digit is 5 because it is green color and the second digit is 6 because it is blue. So decimal multiplier will be 10 power 3 because it's orange color. So tolerance, we can see that is a gold, so it is 5%. So the value of the resistance is equal to 56 into 10 power 3 ohms or 56 kilo ohms with the tolerance value 5%. Here we can have a note, while reading the color code, hold the resistor with color bands to your left. Resistor never start with a metallic band on the left. This is the identification how to see the color codes. Next is temperature dependence of resistivity. The resistivity of a material is dependent on temperature. It is experimentally found that for a wide range of temperature, the resistivity of a conductor increases with increase in temperature. According to the expression, rho T is equal to rho naught into 1 plus alpha into T minus T naught, where rho T is the resistivity of the conductor at T degrees centigrade and rho naught is the resistivity of the conductor at some reference temperature T naught and alpha is the temperature coefficient of resistance. It is defined as the ratio of increase in resistivity per degree rise in temperature to its resistivity at T0 degree. T0. So we can write rho T minus rho naught is equal to alpha rho naught into T minus T naught. So that alpha is equal to rho T minus rho naught divided by rho naught into T minus T naught. For simplification, we can write rho P, that is delta rho divided by rho naught into delta T. The unit is per degree centigrade. So alpha of conductors. For conductors, alpha is positive. If the temperature of the conductor increases, the average kinetic energy of the electron in the conductor increases. This results in more frequent collision and hence the resistivity increases. So that is shown in the graph. Even though the resistivity of conductor like metal varies linearly for a wide range of temperature, there also exists a non-linear region at very low temperature. The resistivity approaches some finite value as the temperature approaches absolute value. As the resistance is directly proportional to resistivity of the material, we can also write the resistance of the conductor at temperature T0 degree centigrade. So RT is equal to R0 into 1 plus alpha into T minus T0. The temperature coefficient can also be obtained from the equation RT minus R0 is equal to alpha into R0 into T minus T0. The same way there we used rho, here we are using R. Then alpha is equal to RT minus R0 divided by R0 into T minus T0, which is equal to 1 by R0 into delta R divided by delta T. Next is energy and power in electrical circuit. When a battery is connected between the ends of the conductor, a current is established. The battery is transporting energy to the device which is connected in the circuit. Now we consider a circuit with a battery of voltage V connected to the resistor. Let the positive charge dq moves from the point A to B through the battery and moves from C to D through the resistor and back to A. When the charge moves from the point A to B, it gains potential energy, that is du is equal to V into dq, and the chemical potential energy of the battery decreased by the same amount. When this charge dq passes through resistors, it loses the potential energy du is equal to V into dq due to the collision with atoms in the resistors and again reaches the point A. This process continues till the battery is connected in the circuit. The rate at which the charge loses its electrical potential energy in the resistors can be calculated. This is only explained over here. The electrical power P is at the rate at which the electrical potential energy is derived. So P is equal to dV by dt, so which is equal to d by dt of V into dq. So V into dq by divided by dt. Since the electrical current I is equal to dq by dt, so the equation becomes P is equal to Vi, where I is the current passing through it and V is the potential difference across it. The SI unit of electrical power is watt. Okay, then by using Ohm's law, the power delivered to the resistance R is expressed in other forms, that is P is equal to IV. Substitute for V is equal to IR. When you substitute, you will get I square R. In the same way, for I we can substitute as V by R. So P is equal to V square by R. Hi students, you all have learned about the Ohm's law and the color code for carbon resistors, how to find out the values. Thank you students. Once again, we'll meet you in the next video. Thank you.